One of the more famous theorems in geometry is if you have a right triangle and an altitude drawn, and let's just say that this is length 4 and this is 9, we can calculate out the length of this line segment. We say that the x is the mean proportional between these two lengths, which means that the equation 4 over x equals x over 9, x squared equals 36, x equals 6 is the length of this side. So anytime you solve an equation like this, it's called finding the mean proportional, or the geometric mean. This theorem could be proved. Most common way to prove it is to notice that these angles are equal and these angles are equal, and there's a whole bunch of right angles here. So let's just say 4, 9x. In this small triangle, the 4 is the short side and the x is the sort of longer leg. But in this triangle here, they're all similar. The x is the short side and the 9 is the long leg. So that's kind of using similar triangles. This can also actually be done with the Pythagorean theorem, although it's a little bit harder. I'm just going to call this A and B. So we would say x squared, a squared plus 4 squared equals x squared, and also b squared plus 9 squared is, a squared plus, let me start that over, a is the hypotenuse. So we would say 4 squared plus x squared equals a squared, and 9 squared plus x squared equals a squared. If I add these together, I get 4 squared plus 9 squared plus 2x squared, this one's b squared, equals a squared plus b squared. Now a squared plus b squared, because it's a right triangle, is equal to 4 plus 9 squared. A squared plus b squared equals c squared. In this case 13 squared, but let's just leave it as 4. Plus 9 squared. So when I simplify 4 squared plus 9 squared plus 2x squared, I'm going to actually multiply this out. 4 squared plus 2 times 4 times 9 plus 9 squared. When I subtract the 9 squares and the 4 squares, I'm left with 2x squared equals 2 times 4 times 9, or x squared equals 4 times 9, or 4 over x equals x over 9 will get me to that same place. You could actually just jump straight to saying, x squared equals 4 times 9 if you ever see a question like this. Usually it's kind of confusing because I'm going to call this A and this B, but you can say x squared equals AB, or let's just call it M and N, so we already use those letters. If you have a rectangle, we can find a square that has the same area as that rectangle. And the way that we do that, the first step is to make a right angle here and make a copy of this side of the rectangle. So some letters here, A, B, C, let's call that D. So BD equals CD. Step 2 is to find the midpoint of this entire line segment and then draw a semicircle. Then extend line BC up, and this line segment here will be the side of the square that has the same area as the rectangle. The reason why that is if you draw, remember, right triangle, and every semicircle you can inscribe right triangle inside, and then we can say, I'll call this X, I'll call this L and W, so this is also W, so we can say that x squared equals LW because it's the altitude drawn to the hypotenuse of a right triangle. If I want to make a line segment whose length is the square root of 6, one way to do that is to start by making a line segment of a little right triangle here with the sides of 1 and 1, and this will have length 2. square root of 2, sorry, because of the Pythagorean theorem. Then if I make a right angle here and make another line segment of length 1 and draw this hypotenuse, just to put this here, if I do the Pythagorean theorem, plus square root of 2 squared equals x squared, 1 plus 2 equals x squared, 3 equals x squared, x equals square root of 3. So that's that. Now I just keep doing this, square root of 4, square root of 5, square root of 6. That takes a little while, but that would work. An easier way to make the square root of 6, or whatever you want, is to make a line segment of length 1, and then a line segment of length 6, and then find the midpoint, make a semicircle, extend, make a right angle here, and extend it up, and that will be the square root of 6, call it x for now, because x squared equals 1 times 6 equals 6, so x equals square root of 6. So that's a way of making a square also. I could also get the square root of 6 some other way, like instead I could start by just finding any two numbers that multiply to give me 6, like 2 and 3, and that would be x squared equals 2 times 3. So it doesn't have to be 1 times 6, but any two numbers that multiply to give you 6. Certainly if the thing is a prime number, you want the square root of 11, for instance, you'd want to go 1 and 11. Big semicircle up here is the square root of 11. A isosceles triangle whose angles are 36, 72, 72, and the sides are 1, there's a way to calculate out the exact length of this base. And it works like this. We bisect this angle, so this becomes 36, and then 36 plus 72 is 1 away, so that's 72. So I'll call this x. So we have these two similar triangles. The big one, which has a side of 1 and a base of x, and a little one, which has a side of x and a base. If this is x, this is also x, because this is an isosceles triangle. This obtuse thing is also an isosceles triangle, so that's also x. This is 1 minus x. So the side over the base, 1 over x, equals the side over the base. And when you cross multiply, you get x squared equals 1 minus x, and you bring everything over to one side, and you do the quadratic formula, x equals -1 plus the square root of 5 over 2, which is about 0.62. So we can actually work out. So we'll see later that this number, 0.62, or -1 plus square root of 5 over 2, is an important number in math, because this triangle is, this 36, 72, 72 triangle is an important triangle, because if I make a regular pentagon in a circle, this angle, this will be a 36, 72, 72 triangle. Of course, this is a 72-degree arc, because it's 1/5 of the circle, and there's a rule that the inscribed angle that intercepts a 72-degree arc will be 36 degrees. So we'll sort of keep this stuff in mind. There is something called the golden ratio. The golden ratio, if I have a line segment here, if I can find a point so that the entire segment over the larger piece is equal to the larger piece over the smaller piece, then this ratio is equal to the golden ratio, or phi sometimes. So if I make AC equal to 1, and I call the entire thing, I'm not doing it that way, right this way. If I call CB 1 and AC, I call that x, and the whole thing is x plus 1, and I do this proportion here, AB x plus 1 over x equals x over 1. Cross multiply, get x squared equals x plus 1. It looks a lot like that other equation, x squared minus x minus 1 equals 0. If I run that through the quadratic formula, I get x equals 1 plus the square root of 5 over 2, which is actually about 1.62. So this number is officially called the golden ratio, but if you subtract 1 from it, you get that 0.62 from over here. So before we had a 36, 72 triangle, which was 1, 1, and 0.62. That 0.62 was minus 1 plus square root of 5 over 2. So if I want to create this thing, I'd want to create this number, and a sneaky way to do that is to make a line segment, is to make a, we want to get a square root of 5, so I make a triangle with a 1 and a 2 there, and that would make this the square root of 5. Then I can draw a little circle here so that if this is 1, that's 1, and that would make this little piece square root of 5 minus 1. And then if I take the midpoint there, that piece will be minus 1 plus square root of 5 over 2, which is our goal. So if I make a circle with radius 1, make a line segment out here, and I create this line segment, which is minus 1 plus square root of 5 over 2, and I make a little circle that's got that length, I'll have created this triangle that I want, the 36, 72, 72 triangle. Once I have my 1.62 triangle, I can get the entire pentagon by finding the perpendicular bisector of the two sides here. Where those come together, it's the center of a circle that would fit perfectly around this this triangle. Now, these perpendicular bisectors, now that I've used them to get the center, I'm going to erase them because they get in the way. And then finally I make two angle bisectors, and this will make my pentagon. So the big step was knowing minus 1 plus square root of 5 over 2 was an important number, and knowing that it's easy to create a line segment that has that length, because all you have to do is make a line segment of 2, a line segment of 1. So that's the square root of 5. Swing this around. So this is 1. This is minus 1 plus the square root of 5. And then the midpoint is minus 1 plus square root of 5 over 2. So that's how we can use the golden ratio to make a regular pentagon.